Hey, astronomy class, how's it going? Happy Wednesday. We're over halfway done with e-learning for this week, so we only got a few more weeks left of school. It's crazy to think about that, but I'm very excited. It's going to be a quick few weeks here, so I just encourage you to take it in and just enjoy what you can. I know a lot of you are probably sick of e-learning by now, and I just want to encourage you to make the best of what we're going with right now. Make the best of what you've got in front of you, and I want to do that with our class. I want to try to focus on the best things that are left for us to learn about, and we're not going to get caught up in a lot of details. We're just going to look at the big picture of what's happening in the universe. That's what we're focusing on this week. And so by the end of this video, I hope that you'll be able to answer this question with some confidence about what is going on in the universe around us. All right, we know that the universe, as we see it, what we see of it, is mostly made up of stars. So if you zoom in right here to the Milky Way galaxy, you keep zooming in, you're eventually just going to see stars. That's what most of the universe, most of the visible universe is made up of. Now, of course, we're talking about the material universe, right? We're not talking about things that we can't see, like spiritual forces and other things that are just invisible to us, right? We're only talking about the material universe, things that we can observe and see, and that's what science is limited to. Science addresses questions about the physical world, not about other parts of our universe, other parts of our existence. So when we're asking this question, what's happening in the universe, we're really talking about the material universe, not what God is doing in the spiritual realms and in our hearts, but really what God is doing in the physical universe at large. And we said that it's mostly made up of stars, and stars are doing this. They are, if you broke up a star into layers, this is like our sun. So the sun has the outer layers, are just kind of relatively cool temperature, and they're made up of hydrogen. That's the outer layers. And then when you get down closer to the core, you have a couple of layers in the core here. You've got hydrogen fusion happening, turning hydrogen atoms into helium atoms. And then the helium core is basically dead weight on a star in the main sequence, like our sun. So helium kind of piles up. It's kind of like ash underneath a fireplace. The burnt pieces of wood that can't be used for anything else. They just kind of pile up, and that's what's happening in our sun right now as I speak. Helium is being accumulated over and over a long period of time, and that over that long period of time, the helium starts to accumulate even more and fill up the core of a star. Now, this is not going to happen anytime soon in our star, according to our models. But over time, helium builds up, and eventually, helium will completely take over the core of the star, which leads gravity to contract the helium core. And because when you contract a gas like that, it heats it up. We've already talked about this, but it heats it up and starts this shell of hydrogen fusion around the helium core again, and causes the star to expand. And then also it causes helium fusion to happen down here at the bottom in blue. So, so this would be what a star would look like when it becomes a red giant, late in its life, after it's already done all of its work on the main sequence, fusing hydrogen into helium. Then the star will start fusing helium into carbon. All right, and that's what's going to be happening when a star has reached the red giant phase. I went through that really fast because we already talked about that yesterday, and I know that what I'm saying right now, it's really easy for it to just become uh, I don't know, just like to become mindless. Like when you hear it, you just don't even really think. So I just encourage you to listen closely and carefully to the different words that I'm using. So it's important to know the difference between hydrogen and helium, right? Hydrogen is one proton, smallest atom in the universe. Helium is two protons. It's the second one. It's the second smallest. So stars fuse hydrogen into helium. Then, when they become a red giant, they fuse helium atoms into a carbon atom, which is six. That's what's happening to red giants. And over time, that carbon core will start to build up. So, this is called the red giant phase. And when that carbon core starts to fill up, Then this red giant star has reached its end. Low mass stars like our sun, anything under 10 sun masses, 10 solar masses, they don't have enough gravity to cause this carbon in the core to fuse into anything heavier, to fuse into any other kinds of atoms. The bigger the atoms get, the harder they are to fuse together. So once a red giant like our sun one day runs out of helium, it's all carbon in the core, then that's the end of this star's life. And that's when some explosions will happen. Gravity will start to contract everything in because there's no more pressure pushing out. And then it bounces out and slowly expands and floats away, leaving a planetary nebula. That is the end product of a low mass star. And then the carbon core, it's so solid and compact that it actually gets left behind, and it's called a white dwarf. So two things come out of a low mass star at the end of its life. You get a planetary nebula, that's the big explosion, and then you get a tiny little white dwarf, that's the leftover core. So here's a little simulation of it. It's not a great picture, and it's not even loading. So, well, it wasn't a great simulation anyway. But if we wanted to trace this on the HR diagram to show where a star goes throughout its life, so it starts out as a nebula up here. It condenses, it gets smaller and hotter. It becomes a star on the main sequence. And then over time, the star will move across the main sequence and eventually become a giant, reaching the red giant phase. And then the planetary nebula and white dwarf happens next. And that what that kind of looks like is for a planetary nebula, it spews off all this hot stuff into space. So it appears really hot. It gets a lot hotter, and then it cools down as a white dwarf. White dwarfs are very, very small and very hot, so that leads them to this corner over here. All right. For other kinds of stars, their path might look a little bit different. So if it's a bigger star than our sun, it might come over here to the main sequence. Might be a bigger giant, but then it still ends up as a white dwarf down here. And so here I showed you this picture, this diagram yesterday. This is a good summary of it all. So out of a nebula come two different kinds of stars: low mass stars and high mass stars. That's what we're calling them. We're trying to keep it simple. In reality, there are other kinds of categories, but we're just keeping it simple here. Low mass is anything under 10 solar masses. So high mass stars become red supergiants. Low mass stars become red giants once they run out of hydrogen to fuse. Then low mass stars, after the red giant phase, they become a planetary nebula, and it leaves behind a little white dwarf. So that's what we learned already. That's a lot of review, but then today we're going to talk about what happens to the high mass star. What's going to happen next to this red supergiant? And it's pretty cool. So just to show you a little comparison here, I want to give you some information about what happens to a star like our sun. So our star is fusing hydrogen into helium on the main sequence, and that's a mistake. It should say 10 billion years there. Good thing I can fix this immediately. So if our star fuses hydrogen into helium for 10 billion years on the main sequence, this is what it does for its adult life. And every time there's a fusion reaction, this much energy gets released. And that's not very much. Electron volts is a very small unit, but that's every reaction. So there's lots and lots of reactions happening every second. But when our sun runs out of hydrogen, it's got to start using the helium that it's made and turn that helium into carbon. And this reaction doesn't produce as much energy, and the star has to do this a lot faster, and because of that, it doesn't have as many years to do that as. So our star will be on the main sequence for about 10 billion years, but then once it's a red giant, it only lasts as a red giant for 100 million years. And once it's fused all of its helium into carbon, it doesn't have the ability to fuse carbon into anything else. It's not possible for low mass stars. So once they run out of helium right here, and they've turned it all into carbon, they're done. And that's when it becomes a planetary nebula and a white dwarf. But here's where something different happens. When a high mass red giant star uses up all its helium in its core, it has so much extreme gravity, so much weight that weight pushes down on the core, the carbon core, and it allows the carbon atoms to start fusing into more stuff. So here's the carbon core, and all of this weight pushing down on the carbon core allows other elements to be fused, whereas in a low mass star, it just doesn't have enough weight to do that. So I want to show you exactly what happens next. So let's say that, remember, for a high mass star, on the main sequence, it doesn't live as long. So let's say that this is like a really big high mass star. It only lives for 7 million years on the main sequence. Compare that to our sun, which is 10 billion years. This is significantly smaller. I mean, um, less than 0.1%, right? Um, of the lifetime. So this is a very high mass star on the main sequence, hydrogen into helium. We already saw how much energy that releases every second. So once that high mass star runs out of its short lifetime on the main sequence, it starts to fuse helium into carbon, and it does that for about 500,000 years, which sounds like, an insane amount of time still, right? But it's very short in astronomy terms, and it doesn't get as much energy out when it does that. Then it has to fuse. The next step is actually carbon into oxygen, so it adds a little bit more weight to it. And it starts to fuse carbon into oxygen, and that it only does that for 600 years. It's trying to do as much as it can, but it's just not getting as much energy out every time. So it goes a lot faster to make up for it, and it just doesn't have a lot of fuel left to do that. So it's kind of scrambling here. It went from 7 million years of lifetime to 500,000 years to now 600 years fusing carbon into oxygen. Once it's run out of carbon, it starts to fuse the oxygen into heavier elements. So fusing oxygen into silicon is the next big step. And there are more steps in here too, but I'm kind of skipping over those. So it only does that for 6 months. The star has to fuse oxygen into silicon, and that only lasts 6 months. It only buys the star 6 months more of time. And it gives it more energy, but the thing is, the bigger atoms are, it's more and more difficult to fuse them since uh, it's more and more difficult to fuse them since the nuclei repel each other even more strongly. So it takes even more energy to keep fusing these heavier elements, and a star just doesn't last as long because it's expensive to fuse oxygen into silicon. It expends a lot of the star's energy, and so it just doesn't last very long, only 6 months here. So the star is now desperate to fuse something else in order to stay alive, and so it starts to fuse silicon into iron, and among other things, and that only lasts 1 day. So once it reaches this point, it's basically almost spent of all its fuel, all of its atoms in the nucleus, atoms in the core of the star are almost done fusing silicon into iron, and it gets energy from that. But again, it takes a lot of energy from the star to do that. And then finally, once the star hits iron, and the weight of the star is pressing down on this iron, it actually tries to fuse iron into anything else, but the problem is it can't. No energy gets released once you hit iron. Iron is kind of like this tipping point where if you hit iron in a star, it can no longer fuse into anything else because it just takes energy to fuse anything into iron, anything heavier than iron. It takes energy away. So this is the point where a high mass star is done, basically over. So here is the core of a high mass star, and it's just the core. Okay, the core is about the radius of the Earth, whereas the outer layers, also called the envelope, is about 5 AU wide. I mean, so the Earth, this is about the size of the Earth, and the rest of the star is like 5 times the distance from the Earth to the Sun away. So, like, this star is huge, but the core is tiny. And inside the core, if you look close, you'll see at the very center of the core you have Fe, which is iron and nickel. So it's called inert, which means inactive, unable to fuse. So it's got this dead iron and nickel core, And then each of the rings outside of that are other elements that are fusing. So you got silicon, oxygen, neon, carbon, helium, hydrogen. Hydrogen's all the way on the outside. And so they're organized by their density. The densest stuff is in the center, right? And this is what our models predict a star's core looks like. Now, it doesn't have these colors, right? These colors are just added for us to see, but this would be the composition of the core of a high mass star. And so it can make all of these different elements using the extreme gravity that it's got. But this core is very, very tiny compared to the whole star. So we're really zooming in very close to the core of a supergiant star here. And these are the different layers of the star's core. It's so big. In fact, the star is so big and the core is so small that if this supergiant was the size of a huge bubble surrounding all of Kai's building, so like completely encompassing the building of Christian Academy, the core, this little core right here, would be the size of a sesame seed. So very, very tiny. Like take a little sesame seed off of a Burger King burger, the bun for a Burger King burger that's got the sesame seeds on it. Take one of those off. That would be the size of the core compared to the entire supergiant star, the size of Christian Academy's building. So very, very tiny core, but that's where all the fusion happens. The fusion happens in the core. So here's another picture of it just to give you another visual. But you've got all those layers. I like to think of stars as ogres because they have layers. It's a reference to Shrek. If you want to be more realistic, stars are like onions, right? Because if you peel back an onion, you get more and more layers, right? Well, if you peel back a star's core, you're going to get all these layers of elements in there. So another thing that I like to compare it to, this is just fun to watch, but I like to compare it to a factory. Stars are kind of like factories because in a factory, you're constantly making things, right? Well, stars are constantly making elements, new elements from the existing atoms that they have. So they start out with just hydrogen and helium, and they create new elements using fusion. They take their gravity that's pushing in and use it to create new elements. And so stars are kind of like factories. They create new elements out of their existing hydrogen and helium. And remember, we're not this in no way takes away from God's work, right? This is how God appears to do it. God creates new elements through stars using the core of these high mass stars. God is able to create new elements, create new matter. Now it's still matter. It existed before, but it's got new properties now because of the star fusing it into new elements. So, last thing, I think, last slide that I have with information, and I got some more pictures too. So once the high mass star hits iron, that's when the fusing stops. No more pressure comes out from the star. So with a drop in the pressure pushing out, gravity wins again. So gravity will take all of those outer layers that are spread out all around the star, and gravity starts to pull all those layers into the star's core. And here's the crazy part: all of that stuff falling into the core of the star, it hits the core and bounces off. So it creates this kind of shockwave bounce effect, and these outer layers just explode out into space. And this explosion is the most powerful explosion in the universe. And it takes the star's elements that it just created and it spreads it out to the rest of the galaxy. And this kind of explosion is called a supernova. We've talked about these a little bit. Let me show you some pictures of some supernovae. It's just incredible. So this is the Crab Nebula, but it's actually a supernova explosion. This explosion actually was recorded in, I think, around the 11th century in China. Some astronomers in China noted that they saw an explosion, and they put down like it's in this part of the sky. And then 1,000 years later, like today, when we look at that part of the sky, we see this, which is just amazing. Like we are seeing the explosion that they saw 1,000 years ago. It's just obviously had some more time to expand. But yeah, incredible. Here's another picture of a supernova. Just the star, as you can see, has just exploded and given up. Another supernova here. This one's kind of irregular. It's got kind of a weird shape to it. Every star is different. Another supernova here. It's just amazing to see all these different stars are just so different from one another. So for a high mass star, what happens when you have a supernova? What happens to everything that's there? Well, the high mass star obviously is going to go up here on the main sequence. When it gets to the end of its life, it becomes a supergiant, and then the supergiant explodes and it ejects all that into space. And then the leftover core, a couple things can happen. We'll talk about this part later, but the main part we're learning today is this supernova, this big explosion that happens. So coming back to this graph here, this diagram, a red supergiant will explode in what's called a supernova. So that is the next step in the process. This diagram is a summary of the theory of stellar evolution, how stars change over time. This is where we're going to stop today. We're going to talk tomorrow or at some point about what comes next. What about the core for the high mass star? It gets real interesting there. So I'm going to put that on hold because I want to give that enough time to talk about. But in summary today, stars spend most of their life on the main sequence. Let me make my face smaller. That's as small as I can make it. Oh, that's fine. Okay. Stars spend most of their lives on the main sequence, releasing energy by turning hydrogen into helium in the core. When the stars run out of hydrogen in their cores, they become red giants and they release energy by fusing helium into other heavier elements like carbon, oxygen, and iron. And so that's why we say that stars are like factories, because they constantly create new elements. So that's all for today. Look at the instructions to see what to do next.